The data reveals patterns we've never seen before in an interstellar visitor. And what researchers find in this 28-hour movie could fundamentally change how we understand objects that travel between star systems. In this video, we will explain what TESS observed, why this footage matters for interstellar object research, and what happens next as 3I/Atlas approaches Jupiter. Let's get started. To understand why this TESS footage matters, we need to grasp what makes 3I/Atlas special. The object was first discovered in July 2025, becoming only the third interstellar visitor confirmed to enter our solar system. The first, 1I/Oumuamua, passed through in 2017 and sparked intense scientific debate about its unusual cigar-like shape and unexpected acceleration. The second, 2I/Borisov in 2019, appeared more conventional, behaving like a typical comet. Now 3I/Atlas has arrived, and it's proving to be different from both predecessors. What makes interstellar objects scientifically valuable is their origin. These visitors formed around other stars in chemical environments potentially very different from our own solar system. They carry information about planetary system formation processes happening light years away. But studying them presents a massive challenge. By the time we discover these objects, they're already moving at speeds exceeding 30 kilometers per second relative to our Sun. We get one chance to observe them during their brief passage through our cosmic neighborhood before they vanish back into interstellar space forever. Previous observations of 3I/Atlas revealed puzzling characteristics. The object displays an anti-tail, which is a spike of material that appears to point toward the Sun rather than away from it like a normal comet tail. This happens when we view the object's debris field edge-on from Earth's perspective, seeing dust particles spread along the object's orbital path. Hubble Space Telescope images captured between November 2025 and January 2026 showed this anti-tail wobbling over a rotation period of approximately 7.1 hours, suggesting the nucleus is tumbling through space. That situation is now changing. The TESS observations provide something previous snapshots could not: continuous monitoring over an extended period, allowing researchers to track how 3I/Atlas evolves as it moves through space. TESS wasn't designed to observe interstellar visitors. The spacecraft's primary mission involves scanning wide sections of the sky for roughly a month at a time, searching for subtle dips in starlight that indicate a planet passing in front of its host star. Each of TESS's 4 cameras captures images covering a massive 24 by 24 degree section of sky, roughly 2,400 times the area covered by the full moon. This enormous field of view makes TESS exceptional at monitoring huge patches of sky continuously, but it also means the spacecraft has relatively low angular resolution compared to telescopes like Hubble. When 3I/Atlas entered the region of sky that TESS happened to be monitoring in mid-January 2026, the object appeared as little more than a bright dot moving across the stellar background. Between January 15th and 22nd, TESS captured the interstellar visitor as it was receding from the Sun, having already completed its closest approach months earlier. The resulting footage shows 3I/Atlas drifting across the frame with its characteristic anti-tail extending toward the Sun behind it. Creating this 28-hour movie required careful processing. Daniel Muthukrishna, a TESS team member from MIT, compiled over 9,000 individual images into a continuous video sequence. Each frame represents a 2-minute exposure, allowing the spacecraft's sensitive cameras to collect enough light from the relatively dim interstellar object. The compilation process involved aligning each image to account for TESS's own motion and the background star field's apparent movement. One significant interruption mars the footage. From January 15th to 18th, TESS entered safe mode following an issue with the spacecraft's solar panels. During safe mode, the spacecraft suspends normal science operations and focuses on maintaining stable orientation and power generation. This 3-day gap creates a noticeable jump in the compiled video, with 3I/Atlas appearing in different positions before and after the interruption. Despite this gap, the TESS observations captured approximately 28 hours of usable footage across the week-long observing window. What researchers found in the TESS data tells an evolving story about 3I/Atlas's activity. The object appeared as a concentrated source of light, with the anti-tail extending in a relatively narrow spike toward the Sun. Due to TESS's low angular resolution, Fine details that Hubble captured remain invisible in the TESS footage. The interstellar visitor doesn't show the dramatic jets, expanding halos, or complex tail structures visible in high-resolution observations. Instead, it appears as a simple bright point with a directional glow. The real scientific value lies in what can be extracted through careful analysis. Researchers led by Avi Loeb from Harvard, in collaboration with Tony Scarmato, plan to search the TESS footage for periodic brightness variations corresponding to the 7.1-hour rotation period previously measured from Hubble images. As 3I/Atlas tumbles through space, different portions of its nucleus or coma face TESS's cameras during each rotation. If the nucleus has an irregular shape, or if different regions produce different amounts of outgassing, the object's brightness should oscillate with the rotation period. Finding this periodic signal in the TESS data would confirm the rotation measurements and potentially reveal new details about the nucleus's shape and activity patterns. The team also expects to see the anti-tail wobbling in the footage. As the rotating nucleus releases dust particles, the anti-tail's position and brightness should vary subtly over the 7.1-hour cycle. Detecting and measuring this wobble would provide information about how dust production varies across the nucleus surface and how the rotation axis is oriented relative to our viewing angle. Interestingly, TESS had actually captured 3I/Atlas much earlier, before anyone knew the object existed. The spacecraft's wide-field monitoring included the patch of sky containing 3I/Atlas back in May 2025, nearly 2 months before the object's official discovery in July. After the discovery, researchers went back through archived TESS data and identified the interstellar visitor in earlier images through a technique called image stacking. By combining more than 9,000 individual frames from May and June 2025, they created a much deeper image that revealed 3I/Atlas as a faint point of light. This retroactive detection provided crucial data about the object's trajectory and allowed astronomers to trace its path more accurately. Remarkably, the stacked TESS images from May and June showed 3I/Atlas appearing as an inactive point-like source with no extended glow or anti-tail visible. This observation is significant because it means the object became active sometime between June 2025 and November 2025, when Hubble began observing the characteristic anti-tail. Whatever triggered 3I/Atlas to begin releasing dust and gas happened as the object approached the sun and warmed up, similar to how comets activate when solar heating begins sublimating ices from their surfaces. This TESS footage matters because it provides the first continuous motion picture of an interstellar object's behavior as it travels through our solar system. Previous observations of interstellar visitors consisted of disconnected snapshots, separated by hours or days. These individual images captured static moments, but couldn't reveal how quickly conditions change or how activity patterns evolve over shorter timescales. The TESS video fills that gap by showing how 3I/Atlas's brightness and anti-tail appearance change minute by minute over a multi-day period. This continuous monitoring allows researchers to measure activity variations that would be invisible in snapshot observations. If brightness fluctuations occur on timescales of minutes to hours, the TESS footage will capture them. If the anti-tail's appearance shifts more rapidly than expected, the continuous coverage will reveal those changes. These measurements directly address fundamental questions about interstellar objects. How stable is their activity? Do they experience sudden outbursts or maintain steady behavior? How does material flow away from the nucleus over time? The combination of TESS's continuous monitoring and Hubble's high-resolution snapshots creates a complementary dataset. Hubble provides the sharp detail that reveals the anti-tail structure and the nucleus's immediate surroundings. TESS provides the temporal coverage that shows how those structures evolve. Together, they paint a more complete picture than either instrument could achieve alone. The pre-discovery detection in May 2025 adds another dimension to this picture by comparing the inactive appearance in May-June with the active state observed from November onward. Researchers can study the transition from dormant to active phases. Understanding when and how 3I/Atlas began releasing material helps constrain models of what ices or volatile materials make up the object's composition. Different chemical compounds sublimate at different temperatures, so the timing of activation reveals what substances are present and how they respond to solar heating. Understanding 3I/Atlas has consequences beyond studying this single object. Every interstellar visitor we can observe thoroughly teaches us something about the diversity of objects drifting through the galaxy between stars. With only 3 confirmed interstellar objects detected so far, we're working with an extremely limited sample. Each new measurement helps answer whether interstellar objects follow patterns similar to solar system comets and asteroids, or whether they represent fundamentally different populations shaped by exotic formation processes. The next major observation opportunity arrives on March 16, 2026, when 3I/Atlas passes near Jupiter's Hill radius. The Hill radius defines the region around a planet where that planet's gravity dominates over the Sun's gravitational influence. For Jupiter, this boundary extends about 53 million kilometers from the giant planet. As 3I/Atlas crosses this boundary, it will pass within 53.6 million kilometers of Jupiter itself, close enough for detailed observations by the Juno spacecraft currently orbiting the gas giant. Juno carries a suite of instruments originally designed to study Jupiter's atmosphere, magnetosphere, and interior structure. But this hardware can also observe 3I/Atlas during the close approach. Juno's optical camera will capture visible light images, potentially revealing details about the nucleus and coma structure. The spacecraft's infrared camera will measure thermal emission, providing data about the object's temperature and surface properties. Particle detectors aboard Juno will monitor the space environment around Jupiter for any material released by 3I/Atlas as it passes through the magnetosphere. Magnetic field sensors and plasma wave instruments will search for any interaction between the interstellar visitor and Jupiter's powerful magnetic field. The microwave radiometer could potentially detect emissions from the object's coma. Even Juno's radio antenna might contribute, either by making precision measurements of 3I/Atlas's trajectory through radio tracking, or more speculatively, by listening for any unusual signals. This multi-instrument approach will provide the most comprehensive characterization of an interstellar object's composition and behavior achieved to date. The TESS observations, Hubble images, and upcoming Juno measurements combine to create an unprecedented multi-wavelength, multi-instrument campaign tracking a single interstellar visitor across months of observations from different vantage points. The data being collected now will be analyzed for years. Researchers will compare 3I/Atlas's properties to the small sample of previously observed interstellar objects and to the thousands of comets originating in our own solar system. Statistical comparisons will reveal whether interstellar visitors are chemically similar to solar system comets, suggesting common formation processes across different stellar environments, or whether they show distinct compositional signatures reflecting exotic origins. The rotation period measurements matter for understanding how 3I/Atlas formed and evolved. Objects gain rotation through collisions during their formation or through gravitational interactions with planets. Measuring the rotation rate and identifying whether it's changing over time provides clues about the object's history and internal structure. The science extends into testing more speculative hypotheses as well. Harvard astronomer Avi Loeb, who leads the TESS analysis effort, has suggested that some interstellar objects might not be natural at all. He points to Oumuamua's unusual acceleration and disk-like shape as potential indicators of artificial origin, proposing that interstellar space could contain defunct technological artifacts or even active probes from other civilizations. While this hypothesis remains controversial and most astronomers favor natural explanations, the possibility drives more thorough investigation. If 3I/Atlas were to transmit radio signals detectable by Juno during the Jupiter flyby, or if it released smaller probes into Jupiter-bound orbits, those observations would revolutionize our understanding of life's prevalence in the galaxy. The TESS footage and Juno observations provide opportunities to search for such anomalies, even if the probability of finding them is extremely low. Beyond these near-term observations, the TESS data contributes to refining our ability to detect future interstellar visitors earlier. The retroactive detection in May 2025 demonstrates that wide-field survey telescopes like TESS can spot these objects months before traditional asteroid survey programs identify them. Developing automated algorithms to search through survey data in near real time could provide earlier warnings of incoming interstellar objects, giving astronomers more time to organize observing campaigns while the visitors are still approaching the inner solar system. Looking further ahead, 3I/Atlas's passage through our solar system represents a preview of capabilities coming online in the late 2020s. The Vera Rubin Observatory, scheduled to begin operations in 2025, will discover interstellar objects at unprecedented rates. Current estimates suggest Rubin could detect dozens to hundreds of interstellar visitors per year once it reaches full operational capacity. Each detection will provide another data point for understanding the interstellar object population. The techniques being developed now to analyze TESS footage, combine Hubble snapshots, and coordinate spacecraft observations will become standard procedures applied to a much larger sample. Within a decade, we may know whether 3I/Atlas represents a typical interstellar visitor or an unusual outlier. We'll understand whether these objects primarily resemble asteroids, comets, or something entirely different. We'll measure the size distribution, composition range, and origin trajectories for dozens of interstellar samples. Right now, 3I/Atlas is speeding away from the Sun at over 30 kilometers per second, its anti-tail glowing in TESS's cameras as it recedes into darkness. In less than 2 months, on March 16th, Juno's instruments will capture the closest and most detailed observations any spacecraft has achieved of an interstellar visitor. Within the next year, as data from TESS, Hubble, and Juno gets fully analyzed, we'll know more about this object's composition, structure, and behavior than we've learned about any previous interstellar visitor. Within the next decade, as survey telescopes discover dozens more, we'll finally understand whether objects like 3I/Atlas are rare cosmic accidents or common travelers drifting through the galaxy in vast numbers. This 28-hour movie isn't just documentation of one object's passage, it's the opening sequence in humanity's systematic study of material from other star systems, physical samples of environments light years away that come to us rather than requiring us to travel to them. And it's happening now.